Hello everybody. I have a new problem set for you. It's going to be number 40 on page 558 and number 68 on page 560. The only other thing for this chapter will be a short quiz, again mainly a drawing quiz, but I wanted to give you some help initially with these homework problems, so I'm going to go through two different problems, probably two different videos. Number 39 right now I'm going to go through. It's on page 558. I recommend you giving it a try yourself, and as I lead you through, it is similar to number 40. It's all about electric fields and how they are basically vectors. Then I'm going to go through a problem to help you with number 68 on page 560. That'll actually be number 38 will be the help with that one. That's all about particle accelerators, essentially. Alright, so let's start with this one. 39 says 2 point charges are separated by 25 centimeters. I've already put it in meters on the board. Find the net electric field these charges produce at point A, then at point B, and then what would the magnitude and direction of the electric force be in the combination of charges would produce on a proton put at A. So let's just start with part A. I want to find the electric field strength at point A. Electric field's a vector. So I have two different charges that create electric fields. I've got a green one and I've got a blue one. I color-coded it for right now. All right? They are negative charges, which means the electric fields are going to point towards them. So if I were to make a little blue arrow for the electric field around the blue charge, that negative 12.5 nanocoulombs, it would be pointing towards the charge, because electric fields travel towards negatives and away from positives. And then if I have the exact same thing over here, I've got a green one, and it is also negative 6.25 nanocoulombs. It is also going to have an arrow pointing that way. Notice I made one larger than the other. The blue charge is closer, stronger field. The blue charge is larger, stronger field. The green charge is smaller and further away, so smaller field, but the fields are going in different directions, and that's the important thing to keep in mind. Alright, so what I need to do is use an equation that will tell me something about field strength, and then I'll find the field strength from each charge. So my equation that tells me about the electric field around a point charge is from one of the first thing the notes I set up. It looks a lot like our Coulomb force equation, but it's missing a charge. So it's going to be K times Q over R squared. So the electric field is equal to the electrostatic constant times charge divided by the distance between the charge and that point that we're trying to measure the electric field strength at. Okay? So I'm going to do this for each charge. I'm going to have a blue charge, so blue field. Alright. And again, it's K times this Q. Alright, for the blue one, it is going to be negative 2.5. And nanocoulomb is times 10 to the minus 9th. Divided by the distance between the charge and that point. So the distance between the charge and point A is 10 centimeters or 0.1 meters, and don't forget to square it. Okay? Now if you plug in K is 8.99 times 10 to the 9th, and to save a little time I'll write that up here. So any place you see K, it is 8.99 times 10 to the 9th, and that's going to be measured in newtons, meters squared per coulomb squared. So if you just plug that in right here, multiply everything out, so that K times the charge divided by the distance squared, you're going to get a total field, let's see here, of 112. Sorry, trying to read off my paper and calculator at the same time. I just did this one. 3 7.5 0.5, and that's going to be measured in newtons per coulomb. And of course it's negative because we have a negative charge right there. All right, then we do the exact same thing. Oh man, get rid of you. You don't need an update. We're going to do the exact same thing for the other charge. All right. Again, K, 8.99 times 10 to the 9th newtons meters squared per coulomb squared. It's just going to be plugged in there. But our charge is negative 6.25 times 10 to the minus 9th coulombs for nanocoulombs. And we're going to divide that by a different distance. So the distance between the blue charge and the green charge is 25 centimeters. From A to the blue charge is 10 centimeters. That means this distance right here is going to be 0.15 meters. Plug that in, and we'll find negative 2497.2 newtons per coulomb. All right, now to find the total charge at A, so it's not the total charge, sorry, to find the total electric field at A, we simply have to combine those two electric fields. Remember that blue arrow and the red arrow are each represented by those numbers. So the electric field total at A is going to be equal to negative 11237.5 newtons per coulomb plus, oh, they're going different directions, sorry. It's the difference between them. Why am I saying plus? So they're going different directions, so they're going to subtract from each other. It's minus a negative 2497.2 newtons per coulomb. And if I combine those two, I'll get an electric field equal to negative 87403 newtons per coulomb. Which direction? The direction of the larger, closer charge. This one right here. That field was stronger, remember? So it's going to be going to the right. So that's the electric field at A. All right, I'm just going to go ahead, erase this. Remember to pause at any point. Doesn't matter when. And I'm going to write up our electric field at A. E at A is going to be negative 8740.3 newtons per coulomb. Right. Erase that. Okay, B is the exact same kind of problem, but we're talking about for location B now. All right, now if you take a look at location B, it's all the way over here. Let's focus on the green charge for right now. All right, that green charge is negative, so the electric field over here at B is going to be pointed towards the green charge. So the field created by the green charge is pointed that way. Okay, and it's close, so that's why I gave it a big arrow. How about the electric field caused by A over here? It's also negative. So over here, point B, A's electric field is also going to be pointed to the right. Those two fields are going to combine. They're not fighting each other, so we're going to actually end up adding them, whatever they may be. Okay, so we have to go through each one again. We're going to find the electric field at point B due to this first charge. So it's going to be K, 8.99 times 10 to the 9th, multiplied by negative 6.25 times 10 to the minus 9th coulombs. divided by the distance between the charge and that point. So the distance between this green charge and point B, that is 10 centimeters, or 0.1 meters. And remember to square it. And if we plug all that in, we find, let's see here, 5,618.75 newtons per coulomb, and that is going to the right. Okay? Now the electric field from the other charge, that negative 12.5 nanocoulomb, again, it's K, 8.99 times 10 to the 9th, multiplied by 12.5 times 10 to the minus 9th coulombs, divided by the distance here. Okay, so this distance is 25 centimeters from the blue charge to the green charge, and then point B is 10 centimeters beyond it. So the distance between the blue charge and point B is 0.35 centimeters. Or sorry, 0.35 meters, or 35 centimeters. Remember to square that. And we're going to get a very small one. 17.3 newtons per coulomb. All right, now both arrows are pointed in the same direction. So instead of subtracting these fields, we're going to add them. And we're going to get our electric field at B is equal to 97.3 newtons per coulomb, which means the electric field at B is going to be 6,536.1 newtons per coulomb. Right. And I guess if you're, noticing, our fields are going to the right and our fields are negative, so I guess that means right is the negative direction in this case, based on how we set it up. So EB is going to the right, and it's equal to negative 6,536.1 newtons per coulomb. All right, there's A and B. Finding electric field strength. Now, the last part is saying, well, let's take point A and B. Let's put a charge at one of those points. And I think it's going to ask us about the force experienced by that charge. So, part C, what would be the magnitude and direction of the electric force this combination of charges would produce on a proton at A? So forget about everything else now. We're going to go ahead and put a positive charge here, a proton. All right, so for part C, force on a proton placed at A. Point A, that is. Okay? So, what do we know? Well, we actually already know that the total electric field at point A is going to be negative 8,740.3 newtons per coulomb to the right. So we could actually go all the way through and find the force that this charge puts on the proton here. All right, and by the way, it's going to pull the proton this way. And then we could also find the total force that this charge puts on the proton at point A, which again will go this way. And use Coulomb's law to do that, then add them together and find the total force. Or we could go a lot simpler route and get the exact same answer just by saying, well, if I know the total electric field at that point, that's going to be equal to the force experienced by an individual charge at that point. Well, what do we have? We have an individual charge at that point. So by doing a little bit of algebra, we can say that force is equal to field strength multiplied by the charge. And I have those numbers. So the electric field strength is negative 8,740.3 newtons per coulomb multiplied by the charge. Now this is a proton. A proton is an elementary particle, so proton P has a charge. So the charge of proton P is equal to 1.6 times 10 to the minus 19th coulombs. That's just a little piece of information right there that I already know. So I plug that in. 10 to the minus 19th coulombs. And I find the force exerted on that charge is going to be 1.39 times 10 to the minus 15 newtons, and it's negative. What does negative mean? To the right. Okay, so that's a particle accelerator problem thrown in with electric field problems, because it's going to accelerate that proton. Hopefully that will help you with number 40 on the homework. Ask me any questions you want, and I'll upload a different video for the next one.